How much money is now on the table?
Yeah, $5 million.
$5 million,
Yes.
just on this table.
Large-scale mining operations are built around one economic principle. The cost of extraction has to stay below the value of what's being extracted. When that equation tips the wrong way, operations stop. Equipment gets pulled out, shafts get sealed, and the site gets abandoned. With whatever couldn't be profitably recovered still sitting in the waste dumps, the tailings piles, the drainage channels, and the eroded hillsides surrounding the old workings. The companies knew the material was there. They just couldn't justify the cost of going after it with industrial equipment. That calculation changes completely for someone working by hand with a pan, a screen, and the knowledge of what to look for. Diamonds and opals are two of the gemstones most consistently left behind in this way. Industrial gold and silver operations had no economic incentive to separate them from the waste stream. Their recovery required a different approach, different tools, and a different eye than what those crews were trained for. The result is that historic mining regions like Nevada, Oregon, Colorado, Wyoming, and Montana contain surface-accessible deposits of gem material that have been waiting for decades inside dumps and tailings piles that most people drive past without a second look. I don't know if you're aware of this, but researchers from the United States Geological Survey estimate that right here in the United States, many industrial mining operations end up leaving behind thousands of dollars in precious stone fragments. Not because nobody knew they were there, but because the operations simply became unsustainable. Expensive machinery, deposits that gradually ran dry, companies that went bankrupt or walked away from the site when the return no longer justified continuing.
But what very few people know is that there are still plenty of opportunities to find precious stones in the areas surrounding those sites. And that's exactly where the individual prospector comes in.
Because beyond the material left behind, the mining operation itself did a large part of the hard work. The machines broke through matrix rock, opened deep cuts, and exposed layers that were previously completely hidden beneath the ground. What was inaccessible became surface, and what was on that surface, diamond fragments, opal, indicator minerals, has been waiting for someone who knows what they're looking at. And that's exactly what you're going to see in today's video. How not to miss the opportunity to find precious stones like diamonds and opals near abandoned mines in a practical and straightforward way, recovering what was left behind a long time ago. And then we'll look at how to identify that material when you're standing right in front of it. To understand why abandoned mine sites are so productive for gem hunters, you first need to understand how historic mining operations worked and what they were designed to ignore. Most mines built before the mid-20th century were single-target operations. A gold mine was there for gold. A silver mine was there for silver. A copper mine was chasing sulfide veins. The crews who worked those sites were paid to extract one thing efficiently, and everything else was treated as waste. The rock that came out of the ground was sorted quickly, often under poor lighting, with basic tools, and by workers who had no training in identifying secondary minerals. Anything that didn't look like the primary target was thrown onto the dump. That dump, technically called a mine tailings pile or waste rock heap, accumulated over years and decades. And in large operations, those piles can span hundreds of feet and reach significant depths of discarded material. Now consider what was actually in that rock. A gold-bearing quartz vein doesn't exist in isolation. It runs through a host rock environment that can include tourmaline, garnet, beryl, topaz, and in some geological settings, corundum, the mineral family behind rubies and sapphires. A copper mine working in the arid Southwest was often cutting through the same volcanic and sedimentary formations, where precious opals form naturally. Because both copper mineralization and opal precipitation depend on silica-rich hydrothermal fluids moving through fractured rock. The miners weren't looking for any of that. They moved through it, discarded it, and kept going. Diamond occurrences add another layer to this picture. In parts of Colorado, Wyoming, and Montana, historic placer operations, the type of mining that uses water to separate heavy minerals from gravel, were set up to catch gold. Diamonds are also heavy, with a specific gravity between 3.5 and 3.53 comma, which means they settle in concentrations similar to certain iron minerals. But a small, rough diamond in a concentrating pan looks to an untrained eye like a piece of translucent or slightly milky gravel. It gets scooped out with the gangue and tossed aside. This happened repeatedly at placer sites in the Rocky Mountain region, where alluvial concentrations derived from kimberlite-bearing parent rocks were being actively worked for gold from the 1860s onward. For diamonds, the key geological signal is proximity to kimberlite pipes or alluvial deposits derived from them. Kimberlite is an ultramafic igneous rock. When a kimberlite pipe erodes, it releases a suite of characteristic minerals called diamond indicator minerals. Pyrope garnet in deep red to purplish red, chrome diopside in vivid green, ilmenite in black to dark gray with a metallic luster, and chromite. When these minerals show up in the waste dumps of a placer operation, it means the alluvial system that fed that operation was drawing material from kimberlite-bearing terrain upstream, and wherever those indicators traveled, diamonds could have traveled with them. For opals, the relevant formations are volcanic tuffs, rhyolites, fractured basalts, and silicified sedimentary layers. In Nevada, Oregon, and Idaho, historic mining targeting epithermal silver and gold veins routinely cut through opal-bearing zones without recognizing them. The waste piles from those operations contain silicified material, chalcedony veins, and nodular zones where opal fill gas cavities and fractures, discarded as low-value gangue. Before visiting any site, research the mining history and primary ore type through state geological surveys. That background tells you whether the waste material at that location has any realistic chance of containing diamonds, opals, or both, and saves you from spending time at sites with no gem potential at all. Once you're standing at an abandoned mine site with the right geological background, the next skill is reading the physical layout and knowing where to focus your attention. The first thing to understand is the difference between a hard rock mine dump and a placer tailings pile. A hard rock mine dump is the waste rock brought out of the shaft and piled on the surface. Angular, irregular material made of broken host rock, vein fragments, and wall rock. Gems appear here as secondary minerals still embedded in matrix, as loose crystals partially freed by blasting, or as material weathered out over time at the pile's surface. The older the dump, the more that freeze-thaw cycles, rain, and oxidation have loosened crystals from their matrix and concentrated them in the finer material at the base. A placer tailings pile is structurally different. Placer operations use water to process gravel, so the tailings are rounded, water-sorted material that has already been separated by hydraulic energy. In these piles, gems appear as loose, often rounded grains that travel through the alluvial system alongside the gold. The hydraulic sorting that water did for the miners works in your favor because heavy minerals, including diamonds, garnet, ilmenite, and spinel, concentrate at specific points depending on how the sluice or dredge was configured. The zones where black sand has accumulated, a mix of magnetite, ilmenite, and other dense dark minerals, are the most reliable indicator that heavy minerals with gem potential are present in meaningful quantities. Near both types of sites, pay close attention to the drainage patterns. Water moving through mine dumps carries fine material downslope and deposits it in predictable locations. At the base of a dump, in any natural depression or channel that collected runoff, the finest and densest material accumulates over time. These natural concentrating points are where small crystals, loose garnet grains, and opal fragments settle, and a careful surface scan followed by basic wet screening of the accumulated sediment can produce results efficiently. And this process doesn't stop at the edge of the dump. Over years and decades, rain and erosion carry residual material from abandoned mine sites much further than most people expect. Fragments of gem-bearing rock, loose crystals, and heavy indicator minerals get transported downslope by seasonal water flow and gradually deposited in alluvial accumulations. Dry gravel beds on hillsides, creek banks, and sediment fans at the base of slopes. These secondary deposits can be located hundreds of feet or even further from the original workings. And because the material has been naturally sorted and concentrated by moving water, they are often easier to work than the dump itself. A dry wash or gravel-covered hillside slope near an abandoned mine site deserves the same careful attention as the tailings pile. Sometimes more, because the water has already done the first round of heavy mineral separation for you. When scanning the dump surface itself, look for shape and structural anomalies, rather than relying only on color or shine. Weathering changes the surface appearance of minerals significantly. A waxy or greasy surface texture in a small fragment, even if it looks pale or unremarkable, is worth wetting and examining closely because water temporarily restores the luster of silica minerals, including opal, chalcedony, and agate. A nodular form, rounded and sitting differently from the angular fragments around it, is the characteristic shape of many opal occurrences. Common opal, called potch, forms in the same environments as precious opal, but without iridescence. Finding potch at a site is a strong signal that the local geology is opal-bearing, and that precious material may be present in the same formation, just below the surface, or in unsorted sections of the dump. For diamond hunting and placer tailing specifically, the approach shifts toward physical testing rather than visual identification. Because rough diamonds in alluvial settings are frequently coated with iron oxide, clay, or silica that completely obscures their luster. What you're looking for is a combination of unusual density for size, resistance to scratching by any common mineral on site, and subtle geometric faces consistent with octahedral or cubic crystal symmetry. In the concentrate pan, these characteristics together, density, hardness, and form, set a potential diamond apart from garnet, ilmenite, and magnetite, even when the visual appearance alone offers no clear answer. Knowing a site has potential is one thing. Knowing what you're actually holding when you pick something up is another. And this is where most beginners lose ground. Not in the field, but in their own hands, when a potentially valuable specimen gets misidentified and either discarded or sold for a fraction of its actual worth. Field identification without laboratory equipment is a matter of applying a systematic sequence of simple physical tests, and for diamonds and opals specifically, those tests are accessible and reliable when you know the right sequence. Starting with diamonds, the first and most important concept to internalize is that rough diamonds almost never look like the cut and polished stones you see in jewelry. A rough diamond fresh out of an alluvial concentrate looks more like a dull, slightly translucent pebble than a sparkling gem. The surface is often coated, the shape is irregular, and the luster, when it's visible at all on natural faces, is what gemologists describe as adamantine, meaning it has a very high, almost mirror-like reflectivity that's distinct from the vitreous or greasy luster of most other minerals. When you clean a rough diamond face with water and hold it under direct sunlight, that adamantine quality becomes more apparent. The reflection is sharp and bright in a way that's qualitatively different from quartz, calcite, or feldspar. The hardness test is the most decisive field test for diamond. No other mineral in common geological environments will resist scratching by a corundum file or by a known piece of quartz. If you draw a sharp edge of quartz across the surface of your suspect stone and it leaves a scratch, you're not holding a diamond. In a field setting, corundum-tipped tools, available from lapidary suppliers, are a more reliable hardness tester than quartz alone, since corundum at Mohs 9 will scratch virtually everything except diamond. If your suspect stone resists a corundum tip, there are very few natural minerals that could explain that result, and diamond is at the top of that list. For opal identification, the approach is completely different because opal is a much softer and more fragile mineral. Its hardness is only 5.5 to 6 on the Mohs scale, which means a steel knife blade or a piece of quartz will easily scratch it. This softness is actually one of your primary identification tools. If you have a suspect silica mineral and a steel file leaves a clear scratch on its surface, you've confirmed that it's softer than steel, which eliminates quartz, chalcedony, and most other hard silica minerals and leaves opal as a candidate. The combination of this low hardness with a waxy to resinous luster and a conchoidal fracture pattern, meaning the broken surface is smooth and curved like chipped glass, is highly characteristic of opal. The water test is the simplest and most immediately revealing test for suspected opal. Wet the surface of your specimen and look at it immediately. Opal, both precious and common, responds to water by temporarily intensifying its surface luster and, in the case of precious opal, enhancing the play of color. A fragment that looked chalky and unremarkable when dry may show distinct color flashes, increased translucence, or a noticeably different surface quality when wet. This temporary change is caused by water filling microsurface irregularities and reducing the scattering of light that makes the dry stone look dull. If wetting your specimen causes any visible change in its optical behavior, keep it and examine it further. The UV fluorescence test is a powerful supplementary tool for both opal and diamond. Many precious opals fluoresce under ultraviolet light, typically showing a white, pale green, or yellowish glow under long-wave UV, and a different response under short-wave UV, depending on the opal's composition and water content. Not all opals fluoresce, and fluorescence alone doesn't confirm the identification, but a specimen that glows under UV in a way that separates it visually from the surrounding host rock material deserves serious attention. Diamonds also fluoresce, typically in blue under shortwave UV, though this varies widely by individual stone. A portable UV flashlight is an inexpensive and highly practical field tool that can help you separate suspect material from common host rock quickly. Beyond these individual tests, context is always a critical part of field identification. A mineral specimen's identity is strongly suggested by the company it keeps. At a Kimberlite-derived placer site, finding Parape garnets, those deep red to purplish grains with a glassy surface, alongside dense, angular, translucent grains that resist scratching, is a much stronger indication that diamonds are present than finding a single ambiguous specimen in a geologically neutral setting. At an opal-bearing volcanic site, finding chalcedony veins, jasper nodules, and common potch in the same formation as your suspect translucent material provides strong contextual support for an opal identification. The geology of the site, the mineral associations you can identify, and the physical test results together create a coherent picture that's far more reliable than any single test applied in isolation. When you find something that passes the basic field tests and fits the geological context, the next step is documentation. Photograph the specimen in place before removing it. Note the exact location within the site, which section of the dump, which layer, what the surrounding material looks like. This information is valuable if you later have the specimen professionally assessed, because a gemologist or a geologist examining your find will want to know the geological context as part of their evaluation. A rough diamond from a known Kimberlite proximal alluvial system and a rough diamond from an unknown source are evaluated differently, and proper documentation of your find protects its provenance and ultimately its value. Throughout this video, you saw why abandoned mines work as natural traps for high-value minerals that were discarded without recognition. You understood how the waste deposits from historic mining operations concentrate diamonds, opals, and indicator minerals in ways that are still accessible today. You learned to read the physical layout of a site, the dump piles, the drainage channels, the black sand layers, and to apply simple field tests that separate rough diamond from common quartz and precious opal from ordinary silica. That's the kind of knowledge that turns an afternoon walking through discarded terrain into something completely different. But here's the part that stops most people cold. You're out there, you found something that passed the hardness test, that showed color under UV, that felt heavier than everything around it. And now you're standing at the edge of the real question: is this actually worth something? And if so, how much? That's where not knowing the difference between a gem-grade opal and common potch, between an industrial-grade diamond and a jewelry-quality rough stone, between a pyrope garnet that signals proximity to kimberlite and one that's just a metamorphic garnet with no further significance. That's where not knowing those differences stops mattering and starts costing you money. People sell gem-quality material for pennies at every rock show, at every informal trade, every single week, because they don't have a framework for evaluating what they're holding. That's exactly why the book Gemology Journey for Beginners, available on Amazon, was built the way it was. It gives you the practical framework for hardness testing, density estimation, luster classification, and color evaluation that you need to make informed decisions before you show your find to any buyer. All explained in accessible language, without requiring a laboratory or professional equipment. If you're serious about working abandoned mine sites and not walking away from your own discoveries with less than their worth, that's the reference you need in your kit. And one last thing before you head out. Never enter the tunnels or shafts of an abandoned mine. Collapses, toxic gases, and unstable ground make those interiors genuinely dangerous, and no specimen is worth that risk. Everything worth finding is already on the surface, in the dumps, the hillsides, the drainage channels, and the alluvial deposits nearby. Stay outside, work the surrounding area, and let the geology do the rest. And if now isn't the right time for that, no problem at all. Subscribe for free and watch the next video appearing on your screen right now. There's a lot more coming on gem hunting techniques, site reading, and field identification. Thanks for liking and subscribing. Good luck, gem hunter.
The mountain calls, it always calls.